So I'm just going to be stood here presenting instead of wandering about like I normally do for two reasons. One, I have to stand close to the mic apparently because they don't have any radio mics. So if I move over here, people can't actually hear what I was saying on the video. And secondly, annoyingly, I've forgotten my slide advancer. So I've got to stand here and actually press the buttons. How 1980s is that? Pressing buttons and stuff like that. It's the first time I've ever given a talk where the room I am actually houses the toilets. And so anybody who wants to go to the toilets to come into your room to use the toilet. I mean, that's not going to be very embarrassing for everybody, is it? Oh, and we can check if he's washed his hands. He didn't wash his hands. Get a picture of that guy. That's just awesome. All right, so we'll make a start. So these are 90-minute sessions, okay? Maybe a bit longer than you're normally used to at other conferences. Maybe you're not. I definitely won't go late, definitely won't run late, because I understand that I am the only person standing between you guys and beer. All right, and that's never a great place to be, okay? So we'll get through it. We'll finish on time. We may finish a little bit early. Depends how much questions there are, stuff like that. But anyway, just in case you're in the wrong room, all right, this is Data Science, Fun and Profit. My name is Gary Short. Anybody who isn't expecting that talk by me can leave now. All right, failing that, you're trapped and you have to be here for the next 90 minutes. All right, so this is me. As I said, my name is Gary Short. I'm a contract data scientist and data engineer. I'm also an MVP in C# because I was a developer before I became a data scientist, as if those two things are separate. You have to do some development to be a data scientist, so that's cool. Data science covers a broad church, all right? To say you were a data scientist is a bit like saying, you're a farmer. That doesn't really tell people what it is that you do. So I mainly specialize in three areas. I specialize in predictive analytics, which is what we're going to be doing today. I specialize in computational linguistics. We'll touch on that a little bit on Thursday's talk when I talk about troll hunting on the internet. So on Thursday's talk, we are going to talk about how we can identify, how we can basically remove all the nasty trollish posts that appear on Twitter and Facebook, how we can make it so that those never appear. Okay, we'll do a little bit of computational linguistics then. I also specialize in machine vision. We're not going to do any of that this week at any point. The most important part of these slides, the bit at the bottom, really, this is how to get a hold of me afterwards when you realise that you had a burning question but you didn't realise it at the time. You can get me on email at gary@derncodingit. See what I did there? That's a joke. There's my blog down there as well. And lastly, is my Twitter handle there at the bottom. I guess everybody's on Twitter now these days. Please feel free to follow me and ask your questions there if you want. I much prefer to answer questions and deal with people initially on Twitter. Not because I'm always on Twitter, it's just that your question can only be 140 characters long if you're using Twitter, and that suits me just fine. Instead of screeds and screeds of emails that basically say, please will you write my code for me? The answer to that question is yes, it will just cost you a lot of money, that's all. But I absolutely will write your code for you. Okay, so what are we going to do here today? Today we're going to do a gentle-ish introduction to data science and all that nice stuff. So we're going to cover a whole bunch of statistics. We're going to cover a little bit on machine learning around Bayesian inferencing. Those things are what a friend of mine calls spell casting. He says you recognize a problem and you go, aha, this is the linear regression spell I have to use here. I shall cast that spell. Okay. The trouble with that is, if I just stood here and went, here's another spell, learn that. Here's another spell, learn that. It's going to be pretty dull, okay? So we are going to do that. We are going to do that. Hopefully it's not going to be dull, all right? But we're going to hang all that stuff on this idea of predicting who's going to win a horse race, right? So we're looking at Prediction, we're looking at predictive analytics, we're looking at predicting the result of a horse race, but we're gonna cover a bunch of statistics and start to get into the machine learning with Bayesian statistics towards the end. We're gonna look at that as well. If you've got any questions, please ask them at the time. Don't feel you have to keep them to the end or anything like that. It's sometimes kind of better if we can get a bit of a conversation going with the audience than just listening to me talk. But if you do want to keep your questions to the end and come up and ask me them afterwards, please do. I'll be here while I'm packing up. I'll also be downstairs afterwards, having a beer or two, courtesy of Amazon afterwards. The sense of the answer that you get varies inversely with the amount of beer I consume. So if you want an in-depth conversation, don't leave it too late in the evening, would be my advice. Okay. So the first thing we want to do is we want to answer this question. What's the difference between a prediction and a guess, right? Because my kids, they make predictions all the time. Oh, okay, they're just guesses, right? The short answer to that from a data scientist, the short answer to that question is about 750 quid a day. Okay, it's the difference between a prediction and a guess. But really, to answer that question, we have to look a bit at probability. The first thing we're going to look at is naive probability, and everybody knows what naive probability is. The formula for naive probability is really simple. It is the number of winning events divided by the total number of events. All right. So the canonical example of that is the fair coin toss. Okay. So if I toss a coin, the number of winning events is 1. You can only win. If I call heads or tails, you can't say heads and tails. Aha, I win. Right? You've got to pick one. All right. So the number of winning events is 1. The total number of events is 2. It can either be heads or tails, and therefore it's 1 over 2. Therefore it's 50%. Okay. You can only use the naive probability formula if all outcomes are equally likely. Okay. That last bit at the end, which says we can only do it if all outcomes are equally likely, means that naive probability falls down fairly quickly. Okay? A great example of where it falls down is if you say to me, well, I'd like you to calculate for me the probability of there being intelligent life on the moon. Okay, I'll say, well, that's not a problem. It's simply the number of winning outcomes, which is 1, because there either is or there isn't, or over the total number of outcomes, which is 2. So there either is or there isn't. Therefore, the probability of intelligent life on the moon is 50%. Right? It isn't, okay? Because there's such a thing as conditional probability. Not all outcomes are equally likely, okay? And that's where we get into conditional probability. And conditional probability is usually expressed in language as using the word given. So, what is the probability of there being intelligent life on the moon given that there's no atmosphere? Okay? So now that we know that, now we can answer the question, what is the difference between a prediction and a guess? So a guess is picking what side of chance an event will fall. Okay? With a fair coin toss, the tosses that came before have no bearing on the tosses that come afterwards. Each outcome, heads or tails, is equally likely, so it really is chance. And if I were to say to you, pick heads or tails, it's really a guess. There's no way for you to predict the outcome of that, okay? Provided you're doing it fairly. If you cheat, of course, then there's absolutely a way to predict it. But that's why everybody always says a fair coin toss. So that is a guess, and a prediction is predicting an outcome, accounting as best we can for all the known conditions. Now you can see the kind of weaselly words that I used there. Makes a prediction slightly better than a guess, but it's still really a guess. The weaselly words there, you know, accounting as best we can for all the known conditions. Given that, we can't account fully for all the conditions, and we don't know all of the conditions. So even if we say, do you know what, there's an 85% chance that this thing is going to happen, still means there's a 15% chance that it isn't going to happen, right? We're never 100% sure, but making a prediction will always be better than making a guess, okay? So, bearing that in mind, let's see if we can get this first bit right, all right? Because a lot of people fall at the very first hurdle, and this is the first thing we're going to do. So, all things being equal, okay, what are the chances of your horse winning the race? Before we account for any of the conditions, what are the chances? What is the probability of your horse winning?
1 in however many horses there are.
Is he right? Yes. Okay, excellent. See, smart people. The number of times that I explain the difference between naive probability and conditional probability, the number of times people say, well, it's 50-50. Your horse is either going to win or it's not going to win. It's like, yes, only if there are 2 horses in the race, right? Is it 50-50? But you're right. So it's 1 over the total number of horses running. And we're going to look at that not because I think you people are stupid and you need to look at it in code, but it gives me a good opportunity to introduce this. And this is a piece of UI that we're going to use just to have a look at that. So when we condition on runners, and it's just exactly as you say, we've got an 8-horse race. So here, before we account for any probabilities or any conditions that we know about, the probability that your horse is going to win the race is 12.5%, right? So if you go to the bookies and it's an 8-horse race, you've got basically no chance of winning, right? If you're just picking by chance, okay? The old pin in the paper kind of thing, like everybody does at the Grand National. I pick this one. Why? Well, because the jockey's surname is my maiden auntie's cousin's surname, therefore my horse must win, right? Which is about the normal level of logic that we all use at the Grand National. Okay. So that's what we're trying to improve on here, all right? So let's pack that away just now. And just to prove that there's no, that I didn't cheat, as if I would. If we just go here and we go condition on runners, which is the one we did there, it's just, what I've done here is I've created some storage for this. I've got a collection of runners and riders. I've then iterated across that, and I've said, you know, for each horse, the chance of each horse winning is 1 over the number of horses that were in the race. Okay, the number of horses that are in that runners and riders. And then I return the probabilities and I graph it. So I didn't cheat, right? I didn't set things up in the beginning just to be like that. We actually did it correctly. All right, so let's pop back to the slide. So we got that right, and I did the demo as well. Excellent. So the first thing we're going to do is we're going to build a model. All right. So that's what we're going to try to do. And the first question is, well, why do we have to build a model? Okay. People in business analytics, business intelligence, well, they don't have to build a model. They've got all the data. And this question, to answer this question, it kind of allows me to explain the difference between business intelligence and kind of data science and predictive analytics. And the easiest way to explain it is to imagine a timeline, right? So traditional business intelligence will look backwards, and it will take all of your data, and it's a very valuable part of data science. It says, look, here's all the data that you as an organization collect, right? It's really complicated the way you've got it all set up and the way you've got it stored, and you can't really gain any information from that, okay? But as a business intelligence professional, I am going to suck up all that data out of the database. I'm going to put it into nice analytics cubes, and I'm going to give you nice fancy graphs and stuff like that, and we'll be able to look backwards and report on what happened in the past, all right? Data science and predictive analytics looks the other way. It takes the same data as the traditional business intelligence people use, all right, but based on that data, it tries to make predictions, all right? So what we're going to do is we don't have the luxury of being able to look backwards to see what the world was like, all right? So what we have to do is we have to use that information, and then what we have to do is we have to build a view of the world. That's our model. We build a view of the world and then see what happens in that world. Okay, we actually test things and make things happen in that world, and we say, look, if we've managed to create this world to look as near enough to the real world as we actually can, there's a high probability that things that happen in that modeled world will actually happen in the real world, all right? And that's why we have to build the model, all right? Because we don't have that, we don't have the luxury of operating in the real world, right? Because we are predicting something which hasn't happened yet, so it doesn't happen in the real world. Having said that, we're going to build a model, usually, you know, makes people very fearful. They don't have to be super complicated, all right? In fact, we'll talk a little bit about what does a predictive model look like. Predictive model is basically everything that we know from past is likely to happen, plus a value to take care of the error we know might be in that model. all right? So our models are stuff we know and the error associated with that, all right? So of course the first question immediately springs to mind as well, if you know what the error is, why don't we just fix the model so the error goes away, all right? And the answer to that question is because it's not always possible, right? Because we're dealing with probabilities and we're dealing with fitting things which are not, so if we have a model, straight line is a good example of that. If we've got a straight line through your points, the points lie all over that line and we draw the best line, right? So we know there's an error there because the error is that not all the points lie on the line, right? There's nothing we can do about that error. We can't change the data to say, well, wouldn't it be better if all the data was on the line? Look, hey, now it's all on the line, therefore we've no error, right? So we have to account for the error. Not all models are super difficult, all right? Average is about the simplest model that we can get, all right? Thank you very much. Average is about the simplest model that we can get, and it's not particularly complicated to build, all right? So let's test our primary school arithmetic, right? Let's see who remembers. Arithmetic from primary school. So if a horse finishes first, fifth, third, seventh twice, second, fourth, fifth, one, first, and eighth in its last 10 races, then its average finishing position is the sum of all of that divided by 10, right? Who thinks that's right? Who remembers that from school? Right? Who doesn't remember it from school and thinks that's wrong? All right? Okay, so that's right. No, it's wrong. All right? What? There's people going, I know, I definitely remember that from school. All right? So here we've got a bit of dubiety, right? We're absolutely right. That is how you calculate averages, okay? But this is where data science and predictive analytics gets a little bit tricky, right? It gets a little bit tricky because data's tricky, right? Data tries to fool us, right? And it fooled us here, okay? So, let me explain. There are basically two types of data, okay? There is quantitative data, and these are usually, there's quantitative data and there's qualitative data, all right? So, quantitative data is normally numbers, all right? It's the length of this thing, it's the distance to that thing, okay? It's the weight of everybody in this room, all right? It's a measurable thing. It's repeatable, and it doesn't matter if you change the units. So if you measured everybody in this room and you measured it in kilograms and you measured it in grams, the number would change, but the ratio would be the same, all right? So if I measured this room and that room and I measured it in kilograms and then I measured it in grams, the numbers would be different, but the ratios between the two would be the same, okay? They are measurable, quantitative things, and more importantly, the difference between, so let's talk about weight, if we're talking about kilograms, the difference between 10 kilograms and 20 kilograms is the same as the difference between 20 kilograms and 30 kilograms, okay? So it's all continuous, evenly spaced. Qualitative data is usually categorical in nature, okay? A good rule of thumb for qualitative statisticians, right? All qualitative data is rubbish, all right? It's all rubbish. Right? Of course, that's not true. There are people who actually earn their living doing qualitative statistics. The point is that it's a different set of statistics. You cannot do the set of statistics that I'm going to talk about today on qualitative data. Unless you cheat, and then I'm going to show you how to cheat later on, right? But as a rule of thumb right now, you need to remember that you can't do the kind of statistical stuff that I'm going to talk about on qualitative data, all right? However, that would be nice if it was obvious like that, all right? But some qualitative data is sneaky, right? Here's an example, and I see this kind of thing all the time, right? So here's a good example. On a scale of 1 to 10, how happy are you with this talk so far? Where, right, 1 is very happy and 10 is, do you have a cigarette? All right, so there's a nice scale of 1 to 10. I might ask everybody in this audience, and I might say, and the average response is 9.9, okay? Because I counted them all up, and I did the division, and I divided it by the number of people here, so the average response is 9.9, right? You cannot do that. Right? I see it all the time. Who's ever been sat in an end-of-year review with their managers, and the managers have gone, you know, we asked, you know, we've done this new model in 360 degrees, and we asked everybody who has anything to do with you to rate your performance on a scale of 1 to 5, and your average performance is 4.6. Who's ever sat in a review like that? Right? Few people. The next time you do that, you can stand up and say, this is bullshit, and I'm leaving. All right? This is why, okay? That stuff, it was just pretending to be a number, right? In fact, 1, 2, 3, and so on, they're actually categories, right? We just happen to have named those categories 1, 2, and 3, okay? And because we did that, it fooled you into thinking that it was actually a number that you could do arithmetic on, like an average, all right? But if I'd called it Tom, Dick, and Hillary, for example, right, then what would the average be? You know, what's the average between, you know, Dick and Hillary? It's a ridiculous thing. And if you're ever confused into trying to think about, is this actually qualitative data or is it quantitative data, think, well, does it make sense for me to change this thing and call it something but by a name? So if you're dealing with actual measurements and you say, well, the distance from here to there is 20 kilometers, and you say, well, does it make sense for me to say it's David kilometers? No. Okay, so it probably is a number, right? But if it's categorical like that, and I've got 1, 2, and 3, he finished first, he finished second, she finished third, does it make as much sense if I called those red, green, and blue? Yeah, it makes just as much sense. So you can actually say, well, actually, that's categorical data. So the trick there is to say, well, no, does it make sense for me to actually name the categories? And if it does make sense, you're dealing with qualitative data, and you can't do arithmetic like that on it, all right? So how do we deal with position and that kind of thing then, right? Actually, I'm going to come back to that, all right? We can deal with it, but we're going to stick with the averages at the minute. If we're sticking with averages, though, then let's actually stick with something that is actually a number, okay? So for this part of the demonstration, we're going to do averages, and we're going to look at something which is a number, and if I look here and I do condition on mile time, so the mile time of a horse is actually a number, okay? It's how fast did he do that mile, right? Now you can measure that in miles per hour, or you can measure it in kilometers per hour, or you can measure it in feet per second, for all I care. It doesn't matter if you change the units, all right? You're still dealing with the same kind of thing, right? It's still going to be a number that you can look at. So this is definitely quantitative data, so we can do average. So what I'm going to do here is I'm going to just show you the code for that. Who here, I should have asked you at the start actually, who here is a developer? Who's used to seeing code? Most people, excellent. Right, put your hands up if you're not a developer. Put your hands up if you don't develop in C#. All right, put your hands up if you're going to be scared if I show you C#. Okay, hey, you think that. You haven't seen my C# yet. I guarantee you, my C# can scare anybody. All right? I'll walk you through it. It's really dead simple, right? So what we're going to do here is, again, we're going to declare some storage that we're just going to put each horse and its probability of winning in. Again, we're going to grab these runners and riders, and we're going to iterate across them. And now we're going to take the average, which is the average mile time. And then we're going to stop and we're going to pause for a minute while I talk about two things. Firstly, I'm going to talk about standard deviation. So remember at the start, we were talking about models. We said we're going to have a model and we're going to have the error, right? And we're going to deal with the error, right? So when our model is average, we're going to talk about standard deviation as being the error. So does everybody remember what standard deviation actually tells us? Don't just nod your head because I'll ask you. Right, so somebody tell me, what does...
The average cat tree.
Yeah, it kind of tells you how spread out your data is, right? And what that means is, if you have a large standard deviation compared to the mean, then you cannot use that, then, it's not, you cannot use it. The larger the standard deviation is compared to the mean, the less accurate your model is as a reflection of the true world, and how less likely it is that your predictions based on average are going to be correct. Okay? So if you have an average, if I take the average of ages, for example, in here, and there's a large standard deviation, and if somebody asked me to predict the age of the next person who comes into my talk, that would be a bad model, right, to use to predict. I'd be wrong more often than I was right. But if I took the average of the age in here, and I looked at the standard deviation, it was really small compared to the mean, then that would be a good prediction model. So the next person who comes in, I say, well, their age is predicted to be, you know, this. And I'd be right more often than I'd be wrong if it was a good model. Okay? That's what standard deviation is. The key point to what I was saying there, the key phrase in what I was saying is relative to the mean. A lot of time I hear people say that, you know, and say, well, you can only use average as a model if it doesn't have a big standard deviation. right? I don't care how big the standard deviation is, right? Standard deviation could be 12 million, right? If the mean is 500 million, then that's small in comparison, all right? But 3 could be a standard deviation, but if your mean is 5, then that's large compared to the mean, so you wouldn't use it. So I don't care how big the standard deviation is, it's how big it is compared to the actual mean. That's the important bit to remember. And the second reason that I've stopped here and paused here is just to point out how crap C# is in certain places, all right? C# here there's an extension method here for collections that allow me to take an average, okay? Does anybody know where the standard deviation function lives in C#? Nope, there isn't one, right? An average is absolutely useless to you without the standard deviation because of the reason that I've just told you, right? Without knowing the standard deviation, I don't know whether the average is meaningful or not to me, right? But there is no function, right, in the base library in C#, right, for doing standard deviation, okay? You have to write your own, or use a maths library or something like that. So let's just drop a little marker there, and we'll come back to that. Let's just have a look at that. Here's how to calculate the standard deviation, by the way, just so we understand where the errors come from. So we're asking this question, if we know there are errors, why don't we just get rid of the errors in the first place? This is kind of where the error comes from. So what we do here in standard deviation is we take the mean and we subtract the average from that, okay, and then we square it, and then we take the average of that, and then we take the square root of that whole thing, okay? Does anybody here know why we do the square, and then we take the square root at the end?
Gets rid of the difference between positive and negative deviation.
Exactly. So what that does is it gets rid of the difference between the positive and the negative deviation. So if you imagine a straight line like that, and that's the points here, you'll have points up here and points down here. Well, if this is the mean, this line represents the mean. If the mean minus this amount, which is more than the mean, is going to give you a negative number. All right. So if you have 2 points and they're both 2 away from the mean, but 2 is more, but one of them is 2 more and one of them is 2 less, if you just added those up, then it cancel each other out, and you go, hey, there's no error. When in fact, actually, there's 4 of an error. Okay. And so doing the square actually gets rid of that, because we all know that 2 squared is, or sorry, the square root of 4 is 2, and the square root of minus 4 is 2, so it gets rid of the negative numbers. But then, of course, because we squared it, we have to square root it at the end to do that, right? Okay, so that's averages and standard deviations. Average is about the simplest. It's about the simplest model we'll be able to use. So let's see if that made any difference. Let's fire up our app. And we make a prediction. This time we're going to make a prediction running conditioning on mile times. And already we've made an improvement, right? Because all things being equal, we said we had a 12% chance of winning, all right? If we only look at the horse's mile time, then we've already made a difference. So horse 1 is out in front there, and we've about doubled our chances of being correct by making that prediction, right? Based on an actual model instead of just on chance of 1 in however many runners we've got, right? So we're making a difference. Let's get back to our slides. No, really, let's get back to our slides. Can I be in charge for a minute? Yes, okay. All right, so let's get back to position. We were talking about position, and a horse finishes first, second, and third, and I was explaining to you why you can't just take the average and say, well, the horse finished, on average, this horse finishes first, all right? But because it's qualitative data, and as I said before, all qualitative data was rubbish, all right? There are statistics you use qualitative data on, but actually we can cheat here as well. We can use these kind of things, we can use this kind of statistics to actually use qualitative data, all right? Otherwise it would be useless to us. I'm not saying we can't use the qualitative data, or in this case the horse's finishing position, but we have to do something with it first, right? One of the things we can do to get around that is called binning, right? I gave this talk in the States at the start of the year, right? And this fell absolutely on the floor, because of course they call that trash in the US, and the guys going bin and trash. I don't get it. I kind of went, okay, never mind. Let's move on, all right? So what we can do is we can literally bin the data by actually saying, well, instead of looking at this horse's finishing position, I can say, I can have a bin for first place, and I can have a bin for second place, and I can have a bin for third place. And every time that horse finishes first, I'll put a counter in the first one. And I can put a counter in the second one when he's finished second, and so on and so on. And then after the season, I can count them all up. And actually, if I start to count how many times he finished first, and how many times he finished second, how many times he finished third, I can then say, well, as a proportion of all of the races where he finished first, second, and third, how many of those times did he finish first out of all the races he ran? So once I actually start counting the number of times that horse was in the category, right, then those are actual numbers. They are actually quantitative data. So we can actually start to use those statistics on that, right? So we can bin the data, and then we can do arithmetic on it, because we then do have quantitative data. Yes?
Isn't this data flawed because, let's say, some horse finishes first, but it's racing with much slower horses. The next race he finishes third, but he's racing with much faster horse, stuff like that.
Yep. So basically, the question there is, the question there was, is that really accurate? Because a horse could be racing against much faster horses and will finish third. The next time he'll be racing against much slower horses and he finishes third. So there's two answers to that. Firstly, we're talking about building a model up, and at the end we'll talk about a kind of unifying model where we'll get rid of those. Because as I'm working my way through, we're only looking at one condition at a time. Okay. And towards the end, we'll look at putting all of these conditions together, but they'll level themselves out that way. And the second one is the frequentist model of statistics would say that will even itself out over the season. Okay, so when you say, well, a horse could have finished first because he's running against slower horses, but every time he finishes first because he's running against slower horses, he's just as likely to finish third because he's running against faster horses. And then over the season, when you do a frequency distribution over the season, you'll get the fair amount. Okay? All right, so there's two ways of answering that. All right? So let's look at what that actually means. So actually binning the data, let's have a look and see what that actually means. So if we jump down here to the code, and we say, down here, condition on the finishing position. So now we are actually using finishing position, which was qualitative data. Again, we build up a store here. We get our runners and riders, okay, and we iterate them. We iterate through that. What we do is we create some storage for the number of firsts, and then we iterate each horse. We get the finishes, and we collect all of the first places, okay, because that's what we're interested in. We're trying to predict the winner, right? So we get all of the first places, and then we count them. And then that horse's probability of winning is actually the number of times he finished first in the season divided by the number of times that he finished a race. Okay, and that'll give you the probability of winning. And the answer to your question is that should have balanced out. You know, he finished first because he was slower horses versus he finished third over faster horses. Should balance itself out over the season. Okay, it's probably not so accurate at the start of the season. Right? And then what we do is we add that probability. So we say we'll take our horse and we add that probability of the win into our storage. And then we're going to introduce you to something called unity. We have to unify these probabilities, right? And what that actually means is probability has to range between 0 and 1 or 0 and 100%. Okay? It's usually expressed either in percentage terms or as a decimal between 0 and 1. And that is because 0, in probability terms, 0 is there's absolutely no chance of this event happening, right? Like the Earth exploding tomorrow, right? There's like a 0 chance of that happening. Versus 1, which is a 100% chance, is absolute certainty that will happen. Like tomorrow we'll get here, right? The Earth will not end over tonight, there will be a tomorrow, okay? There's a 100% certainty of that. If we just did that, okay, and then we did that sum and we added it up, if they all won across all of the probabilities for all the different horses, right? We have a chance, if we're summing things together, that actually bursts that 100% ceiling. You can't have a 120% chance of your horse winning. Okay, so what we have to do is we've got a collection of numbers, okay, and they all must, none of them can be greater than 1. Okay, so what we want to do is we want to make sure that none of them exceed 1, but we also want to make sure that the differences, the differences in the two values remain the same. All right, so if I've got something that is 1 and a number which is 1.5, okay, I want to get rid of that because it's wrong, but I still want to make sure that the first value is 50% bigger than the second value, okay, when I reduce everything down. And the way to do that is a function called unity, and it's quite a simple formula actually. What you do is you divide each number in the collection by the sum of the collection, okay. That way what happens is that you ensure that when you total everything up, you're still only going to get 1, but that you've maintained the magnitude between each item in the collection. Okay, does everybody understand A, how to do that, and B, why we do that? Yep, okay, awesome. So the bit that does that, again, is really simple. So what we do is we just get the sum of everything in that collection, and then we walk through that dictionary, okay, and we create a new collection called clean probabilities, where we actually do that sum, where we take each of the values in the collection and divide it by the sum, and then we add that to the new probabilities, and we return that, and then we can get a probability based on finishing position. Okay, so that is only looking at finishing position. So if we looked at finishing position, we can see over there horse 3 is now up to nearly 30%. Okay, so we've almost increased our chances of winning by like 150% as to where we were before. Okay. Let's see, how are we going for time? Good, plenty time left. Okay, any questions so far? Nope. All right, let's crack on then. Again, this is one of the reasons. This is how we're going to answer. Another way we're going to answer your question. So, can we take this, everything that we've learned, all of these different models, and can we unify them into one particular model, right? And that's quite big in data science just now, where we say, well, we've got lots of models that model different aspects of making predictions, and we say, well, that's great, and they're all very good at that one narrow thing, but is there a way of combining all of these models together to actually come up with a unifying model that it kind of explains everything that we want to do about this thing? And the answer to that question, of course, is yes. Otherwise, I wouldn't have asked it in the first place, because it's a bit dull going, here's a question, the answer is no, let's move on. Okay, so what we're going to do is unify the probability. So how we do this is we run each of the models, okay, and we get 3 basic probabilities, okay, of things which are going to happen. At this point, we can, if we want, apply any weightings that are required. So this is the next new thing that I'm going to introduce, this kind of idea of weighting, is that when you're unifying models together, okay, if you know that a particular model performs really well, it doesn't answer all of the edge cases, which is why you're trying to fold in other models, but it does perform really well, then you have the opportunity of expressing that difference in performance inside this new model by adding a weighting. And all you really do to add the weighting is to go through that particular model and inflate them all relative to the others by a particular weighting. And obviously, that's going to be more art than science, okay? You're going to start off by doing too much and then too little, and then you'll probably settle for a kind of magic figure, and then you'll give that some meaningful name, and in years to come, people will say, how did you come up with that? And you won't be able to remember that it was actually just a guess, okay? As a lot of stuff is in data science, right? It's just you have to have a feel for the data, right? And say, I think it's this. But you have an opportunity here to add those weightings. And in the same way you have the opportunity to actually, decrement the weighting of other models as well as inflating others, all right? Bear in mind that's kind of a different effect. Inflating the results of one probability model isn't necessarily, so let's say you inflate one probability model by 2. It's not necessarily the same as deflating another model by 2. That might have a different, more subtle effect. It isn't necessarily the same. So you can add, you can inflate and deflate models in that kind of weighting part. And this is where your A/B testing and all that kind of thing comes on. You know, if you run 2 of the unified models, one with particular weightings, see which one prefers, see which one performs better. Okay, so you're going to go through a period of testing and examination there. But that's the next stage then, is to add that weighting then. And then what we do after that is we stitch those models together, okay, just by basically taking 3 lists of probabilities and making one big list of probabilities out of it. And then what we're going to do is, now of course we have to work out, we have to sum up those probabilities for each of our horses. So what we do then is we grab that collection that we had and we group them by the horse name. So now we're going to have the horse name and the whole bunch of values for each of the probabilities from each of the models after it's been weighted is going to be there. So we're going to group those together, and then we're going to iterate through the grouping. What we're going to do there is we're going to take the horse from the first one, it's going to be the actual horse, and then what we're going to do here is we're going to sum up these probabilities, and we'll get that by passing in the probability and then summing the values. Okay, that's how we do that. And then of course, because we've done that, because we've summed up all those values, right, there's a chance then, in fact there's an almost certainty, that we're going to burst that 100% ceiling and end up with something ridiculous like this horse has a 360% chance of winning, right, which is clearly nonsense. So what we need to do there is to unify those scores back down again, which, as we said before, is just something which will maintain the difference between 2 values, but make sure that they all sum up. Their sum doesn't go past 1, and we'll return that. So if we run this now, we get this idea of this unifying probability, which has all of our models all folded in together, and with weighting ones that we know performed particularly well, which in our case before, the one that performed particularly well was the horse mile time. Okay, so we weighted that a little bit, all right? And now we see we've gone here, we've got our horse up to 22%. Remember, we started at 12. So we've practically doubled our chances of winning, you know, using statistics as opposed to just guessing, all right? Which may not seem like much because you've still only got a 22% chance of winning, all right? But if you're a gambler and you're using statistics, what it means here, if you're using the frequentist approach, you know, if I gamble enough times using this, then I will win more often than I lose. In any given day, I may have lost, but taken over a year, I will win more times than I lose, okay? Even here, even though you've only got a 22% chance of winning this day, it's still double your chances of winning just by chance, all right? So we have improved our score. Yes, sir?
Is horse 1 coming first in the race, or is horse 1 a particular horse in the race that you're applying this to?
It's horse 1 is a particular horse in the race, not necessarily the one that won. It's just that I have no imagination for naming horses, so I named them horse 1 through 8 because I'm an engineer.
So you're saying if we apply the model to horse 1, you get a 22%
Yeah.
chance of
Exactly.
right. However, if you applied it to horse 7, there's still only an 8%.
Yeah, there was only an 8%. So horse 8 dropped actually from being 12% down to 8%, whereas horse 1 went from that 12.5% to 22% when we actually applied each of the models. And you can see as we applied each of our statistical models that we've learned as we've gone along, from average to qualitative to quantitative statistics, we came upon a new spell, right? And as we applied that new spell to our problem of prediction, different horses were coming out. So we wanted a unifying model, which is quite big in data science just now. So that's why I included it in this talk, because it's quite big in data science. But also it makes a lot of sense. If we have maybe 4 or 5 models and they're all predicting different winners, then that's showing that we're conditioning for different things each time. So maybe one model will condition for the horse's mile time, another model will condition for the jockey, another model will condition for the type of going, another model will condition for the race track. We want to fold all those in. We don't want to just go, well, we're only going to condition on this, we're only going to condition on that. We want to fold those all in to one unifying model so we can condition on everything. It also helps with the question that this chap had earlier on. It says, you know, if you're doing averages, for example, or binning, for example, then the frequentist model says, you know, over the season that will average itself out and it'll be fine, and that's true and that's cool. But I still want to make predictions on like day 4 of the season. You know, So I can't wait for the frequentist model to balance itself out. I need to fold in more conditions. And as using that particular binning model, I know as a statistician that the frequentist model says as the season goes on, this is going to balance itself out and become more accurate. But at the start of the season, it's going to be less accurate. So that's where I'm going to use that weighting part, right? So I'm going to decrement the weighting of that. I'm going to put less emphasis on that model at the start of the season, and I'm going to put more emphasis on that model at the end of the season when I know it's going to start to come good. All right? But yes, to answer your question, they're not places, they're horses' names.
Can we really say we've got 22% chance of winning? Isn't that just if we look at that data point? Don't we have to take into account the other?
No, because that was the whole, that 22%, that was from the whole unified model. So that was its overall probability folding in all the models we've done so far.
Okay. So what does the, if we go back to the previous diagram then, what does the horse 8 represent then?
Do you want me to, right, so if I go back here, right, and fire this up. Did I actually press that button? No, and I ask it for the unifying model.
Yeah.
Right, so horse 8, what does that horse represent? That horse represents a horse that I could have named Charlie, and I'm now wishing I had. Right? But I didn't, because I've got no imagination, and I just named it horse 8, right? It's just a horse in the race. There are 8 horses in this race.
Yeah, no, I understand that bit. So what does the 6.4% next to that horse represent then?
That is its prediction of winning. So it's got a 6.4% chance of winning based on the unified model that we've got.
Right.
Based on the conditions. So remember right back, start of the talk, I was talking about conditional probability. And here now we've folded in maybe 3 or 4 by this time conditions. Okay. So based on those 4 conditions, I believe that horse 8 has a 6.4% chance of winning, whilst horse 1 has a 22.39% chance of winning. But remembering, there's no way that I've accounted for all of the conditions, right? It's just the conditions we've looked at, this is the result. Yep? Okay. Anybody else? No? Alright, let's crack on with more stuff. Oh, actually, let's shut that there. Alright, let's go back to their slides now. So that's that. Okay, so going on before, there's a lot of art, and there's a lot of art as well as science that goes into data science. Okay, so one of the things that we have to deal with is pretty much like you just said there. Is that everything that could possibly happen? And the answer to that question is no. It's just there by the time we're finished 3 or 4 conditions that we looked at. All right. And the question is, well, how do we know that a condition is actually significant or not? Okay. I mean, we might pick jockey, we might pick race course, or you know, the actual trap out of the, I don't even know if that's the right word, but you know the boxes that they put the horses in to start them off. I'm going to use trap because that sounds good. You know, so the horse may favour the inside or the outside, right? We don't really know. And at the minute we just kind of pick them, you know, at random. But actually, is there a way that maths can help us actually come up with the proper variables to use? And the answer to that question is yes, it can. So we can open up Excel here, because Excel is our friend. Is the friend of the data scientist. And while that's opening up, too late, I'm going to pour some water anyway. So here what I've got, yes, thank you very much for telling me about Power Query. I don't care. So here we've got 2 variables. The distance over which the horse ran and the temperature on the day. And the question is, can we work out, you know, is there a mathematical way of deciding which of those is relevant and which is not? Now, I've made it distance and temperature because we can see that, you know, intuitively we would think that the temperature wouldn't really have much bearing, whereas the distance clearly would, because we're not going to ask a horse to run for so long that it's going to be affected by heat exhaustion or any of that kind of thing. We're talking about, you know, reasonable races. So intuitively we feel that distance will have more of an impact on the result than actual temperature, but can we prove that mathematically? And the answer to that question is yes, we can. There's a thing called the correlation of coefficient. It's not, it's the other way around. It's the coefficient of correlation. See, it's too late in the day, right? There's a thing called the coefficient of correlation, and basically what it does is it tells you how correlated 2 variables are. Okay. Now, luckily for us, there is a function in Excel which will do this for us, right? So if we take, it's called correl, so we can ask it to say, what is the correlation between whether or not the horse wins and the distance? And here it says it's negative 0.8, okay, the coefficient of correlation. Now, I'll come back to that in a second. We're just going to do exactly the same thing over here. So if we take this, again, and we ask Excel to tell us what is the correlation between by winning or not, and the temperature, and Excel will tell us that the correlation is 0.4%. Okay, so let's dig into these numbers a little bit and explain what that actually means. So, first of all, the negative sign here is nothing to do with magnitude, right? It tells you the way in which the two items are correlated. Okay, so if something is positively correlated, okay, they move up and down like that together. Okay, if they're negatively correlated, as one goes up, the other goes down. Okay, but the correlation is still the same, right? So a concrete example of that would be to look at temperature and ice cream sales. Okay, so in the summertime, for example, temperature and ice cream sales will go like this. You know, as the temperature rises, ice cream sales will rise. As the temperature drops, ice cream sales will drop. So they are positively correlated. If you look at temperature and tea bags, for example, they'll be negatively correlated. As the temperature climbs, less people want warming cups of tea. As the temperature drops, more people want cups of tea. So they go in the opposite direction. So that's all the negative part tells you, the actual direction of the correlation. It's nothing to do with the magnitude. So then we're left with the actual number. And in data science, in statistics in general, a coefficient of correlation of 0.6 and above means it's significant and you should use it. All right. There is every rule has an exception, and I'll come back to that exception. But 0.6 to 0.6 and above is something you can use. We tend to aim for around about 0.8. If it's 0.8, then it's really good, but we can use it if it's 0.6. So actually, doing this exercise here will tell us that we can use distance because it's got a coefficient of correlation of 0.8. We can't really use temperature because it's got a coefficient of correlation of coefficient of correlation of 0.4. Okay, so it's not really significant. It has no real bearing on what happens. So just from doing that, before we even start to build our model, we discard temperature, right, and we would go with distance. So there is a way mathematically to actually pick out, you know, of the 10,000 things that might go into winning a horse race, we'd actually sit and we can model all these going, no, we're not going to use that one, we're not going to use that one, we're not going to use that one, we're not going to use that one. Okay, we are going to use this one, we are going to use this one.
Those would be useful for setting the weighting then. So you could potentially include temperature, just weight it a lot lower than distance.
Yeah, exactly. So that might, that's a great point. So what the gentleman said there, just for the benefit of the camera, is that, you know, you could actually use this for doing your weighting as well. When you're building that unified model and you want to weight the differences in the model, and you don't really have any good A/B testing to say that one performs better than the other, you have a feeling, intuitively you think, you have a feeling that it does, but you don't actually have the numbers to back up because you haven't done A/B testing, then you can say, well, what actual conditions go into model 1 versus what conditions go into model 2, and you could run this kind of thing here, and then you could use the differences in the coefficient of correlation to be a starting point for your weighting. Yep, absolutely. So I said there was an exception to that rule, that kind of 0.6 and above rule, and that is if you're doing psychology or sociology, or basically if you're doing statistics on human beings, because human beings are deemed to be, in fact not deemed, experimentation shows us, not that we like experimenting on humans, but experimentation shows us that humans behave in such a random way anyway, that actually if you've got a correlation of 0.4 or above, it is actually significant. So in the field of psychology and sociology and criminology and that kind of stuff, a coefficient of correlation of 0.4 will allow you to continue using that variable. But since we're not talking about human races, we're talking about horse races, then we'll stick with that.
So is it out of 1? Is it between -1 and 1?
After all that great dramatic pause, the answer to that question is yes.
I'm just wondering to get the correlation between the wind conditions and the distance, what would you have to do to actually make it 1? It seems that you can see there when you see.
There have to be. So the question is, what would 1 look like?
Yeah.
right? If there was a one-to-one relationship. So again, take it nice and simple, right? If I sell ice creams and for every degrees rise in the temperature, I sold one more ice cream, right? And for every fall in temperature, I sold one less ice cream, okay? And they went up and down in the same units like that, that would give you a coefficient of correlation of 1. They're exactly correlated, right? Whereas here you can see, you know, there's some gaps in there, the temperature goes up and down and has no real bearing, and all of a sudden it'll hit a kind of magic bit and the horse will stop winning, and then it'll kind of, sometimes it'll win at one temperature, sometimes it'll lose, so there's not an exact correlation, and therefore it's dead. Yes, sir?
What do you do about the fact, I mean, looking at that, you can fairly easily see that the horse is just crap at running over 900 metres or 900, whatever it is.
Mm-hmm.
What do you do when, how can you sort of take that into account mathematically? Because looking at it, you can see that, well, this horse is basically guaranteed to win if it's running up to a 900 metre race, and it's never going to win if it's running more than that. Do you
No. That would be so. See, this is why data science is hard. That would be true if the coefficient of correlation was 1. If this exactly matched real life, right?
If you did
But it doesn't, so you've got variance.
If you did it only on the 100 to 900 subset, then you would get a correlation of 1, wouldn't you?
But that's only one feature, one variable. First of all, second of all, as he said, it's not 100%.
I'm not sure what your question is. I think, is your question saying how do you get 1, or how do you actually use this?
I think maybe I can talk to you at the end because I'm not entirely sure what I'm asking yet.
Okay. Okay. At this stage, all we're using this for is to say, does this condition have an impact on the result? We're not saying what that impact is. It's just saying, does it have a significant, for the data that I've sampled, for the data that I've got, does this condition have a significant impact on the result?
Okay.
And the answer to that question, because the first column, distance, has a coefficient of correlation of 0.8, then it is significant, and that's all. So we've answered 2 questions there. Does it have an impact? Yes. Is that impact significant? Yes.
Yeah.
We haven't yet answered the question, what is that impact? All right?
Can I add something?
Yes.
Just for him. This is really oversimplified example, and I can quote one professor from Stanford talking about data science, that actually the amount of data that you have is more important than the actual algorithm or model that you're using. So if you have really a small amount of data, it's never going to be correct. Or at least on real data it won't perform as good as like
So there's 2 things there.
Yeah.
So first of all, I absolutely agree, right? I will take more data and a weaker algorithm over less data and a stronger algorithm every day of the week and twice on Sunday. Okay? There is a way of testing how significant your findings are. So you can have a small sample. There are ways around that problem. Is basically what I'm saying. So if you sample your data correctly, if this was a random sample of a small number of races, it would be fairly meaningless. But if this was a random sample of every race that had ever taken place, then the findings would be. Or if it was statistically modeled correctly, so that we actually took a sample. So if we said, we know, for example, in the population of every race that had ever been run, right, there is 5% of the winners are grey horses, right? If we sample and we say, right, I need in my sample 5%, so we actually make our samples look like or have the same ratio as what the actual population does, then we can be more confident in our results, right? But this gets back to this idea of model plus error. It's important to understand what the error is, all right? So you're right in as much as this is oversimplifying it, because I don't want to confuse you with too many things at once, all right? But it's not correct to say that, therefore, it is statistically insignificant. We can actually say, or we can actually ensure in our sampling that it becomes significant if we sample correctly. Okay? But sometimes you can't sample correctly, right? Sometimes you can't take the whole population, right? Because either it's just far too big to process, although that problem is going away so much now, or we just don't know. Like, so if I said to you, what's the result of every horse race ever? I don't know. Does anybody actually record every single horse race for the entirety of time? So we might not be able to take the whole population. All right. So sometimes we can't, but where we can, if we sample properly, then we can fix the problem with small amounts of data.
That's a quick question on this.
Yes.
So I can't totally see the spreadsheet, so apologies if I've got the wrong idea. First column, we've got win ones and zeros in it.
Yes.
Isn't it a little bit difficult for us to deduce a meaningful linear correlation here when we've got what is essentially quantitative data in the first column, right? So we've got true false against numerical data.
So the answer to that question is yes, and we're going to come to that.
Okay, fair enough. Quiz no further.
Yes. So the answer to the question is yes, but bear with me. I like it when people ask questions that get answered later on in the talk, because it means I'm on the right track. All right, don't save that. All right, so we got a little bit sidetracked there, but the question we were trying to answer there was, is there a way mathematically to help us actually choose the variables that we were actually conditioning on? Because at the start we were just kind of taking them by random, and we want to say, well, that's fine. If we've only got 5, we can use them all. If we've got 10, we might just randomly sample them, and chances are we'll get it right. But if we have 10,000 variables, then we need a way of knowing which ones are right and which ones are right. Okay, this is how we're going to do it. Right? Just a recap before we move on, because we did kind of get, interesting though it was, we did kind of get sidetracked a little bit there. All right, so that's all very well, but we have to. One of the things when you're using this method, right, of the coefficient of correlation is you have to be careful of confounding variables, right? And confounding variables is quite an abstract thing to explain, and it's easier to explain with a concrete example. So the concrete example is ice cream sales and drownings, okay? Now it's a fact that ice cream sales and drownings are positively correlated, right? The more ice cream sales there are, the more people drown. Okay, the less ice cream sales there are, the less people drown. Okay, but that does not mean that you can stop people drowning by closing all the ice cream shops. Okay, because there is what's called a confounding variable there, which actually both of those variables that we're looking at are actually positively correlated to. Okay, and that is temperature. So as temperature goes up, the number of ice cream sales goes up. As temperature goes up, the number of people who do stupid things to cool down goes up, and they drown. All right. So the temperature there is the confounding variable. Now I picked a simple concrete example, and it was easy to spot what the confounding variable was. What you have to be careful of is that there's not a confounding variable in those things that you're looking at, which is actually driving a correlation, when in fact both things are actually correlated to another confounding variable. Sometimes, of course, having said that, it doesn't actually matter. Right? Sometimes it does. Sometimes you actually need to know what that confounding variable is. Other times you don't really care, and it depends what it is you're trying to achieve. So to go back to our concrete example of ice cream sales and drownings, okay, if we're trying to stop drownings, right, then we do need to know what that confounding variable is, right? Because otherwise, if we didn't, we just close all the ice cream shops and we think we'd fix the problem, and in fact, we haven't fixed the problem at all. But if all you actually want is an early warning to drownings, okay, then seeing ice cream sales rise can make you think, I need to get more lifeguards around the pool and pay more attention. So it depends. Okay, that's kind of a contrived example, but you take the point. If all you're actually looking for is kind of early warning, then you don't actually care that there's a confounding variable. If one thing goes up followed by the other thing going up, and all you want to know is to predict that other thing going up, this is an indicator of that. You don't actually care whether there's a confounding variable or not, right? Yes?
So that example, temperature is the confounding variable.
Correct.
Okay.
Because both ice cream sales and drownings are actually not correlated together, right? Nobody drowns because they've had an ice cream or vice versa. They drown because of this temperature, right? Because they're trying to cool off. And they buy ice cream because they want to cool down. So drownings and ice cream sales, although they look to be positively correlated, are actually correlated with a third variable. Both of them are correlated the same with the third variable, which makes them look like they are actually So that's what, so you have to watch out for. Bearing in mind, sometimes you don't care, but if you do care, you know, just think to yourself, is it possible there's a confounding variable at work here? Okay. All right, so after all that, sorry, for you guys at the back, that actually says we're not all data scientists, just give me a formula for predicting winners. All right, so what we're going to look at here is we're going to stick with this idea of ice cream sales because it's easy to understand, and I'm going to show you a technique. And I'm going to use ice cream sales, but it applies here. So if we grab this and we go to our linear regression example, and we can use Excel here because Excel makes it easy. All right. So what we've got here is ice cream sales. All right. And we've got temperature here. And what we want to do is actually to be able to predict ice cream sales based on the temperature. It's kind of the same thing as horse racing. All right. And then we'll get to answer your question at the end. Right. So how we do this is we can hit the data tab here, and we can use data analysis. Now this is actually an add-in. So if you go to Excel and you click on the data tab and you don't have the data analysis add-in, then it's just an add-in. If you go into options and add it in the analysis toolpack, you can add that in if it's not already there. Kind of depends if the person who's used your Excel before, whether they had it when they installed it or whatever. But anyway, once it is installed, we can select regression here, and you can say to Excel, hey, I would like to do a regression. And Excel will say, certainly. What would you like to do? And I say, what I want to do is I want to predict ice cream sales. And I would like to predict that as a function of the temperature. Thank you very much. And since you seem to be unable to tell the difference between strings and floating point integers, I'll tell you that the first column contained labels, because you don't seem to be able to work that out for yourself. And what I want you to do is to work all that out and stick it in a new spreadsheet for me, stick it in a new worksheet for me. And Excel does that, and isn't that lovely? Okay, so there's two things that we want to be. What we've done there is a linear regression. So what we did there was that linear regression model. And before we make any predictions on our linear regression model, yeah, this projector screen could be doing with being a bit higher, couldn't it? Don't be afraid to stand up if you want to see the bottom of it. It's not the best kind of projector, but it's all we've got. But as I say, don't be afraid to stand up and walk around so you can see it. We have to check two things, right, before we know that we can make any predictions based on this regression, right? Two things we're going to check here are this value here, r squared, and r squared tells us what change in the variable that we're trying to predict is accounted for by the variable that we said we wanted to use as a function. Okay, so that's the abstract. The concrete is how much of the change in ice cream sales is actually accounted for by the change in the temperature. And here it's 90%. So most of the change in ice cream sales is accounted for by change in the temperature. So that's good. And the other thing we want to change here, to check here, is this p-value, right? And this p-value tells us whether that change is actually statistically significant. Because what it actually says is, what is the chances of that change that we're seeing? What are the chances of that being down to just blind chance, just blind luck? And actually, you can see here it's 2, it's 0.5%, right? So 0.5% chance that this change that we're seeing is actually just down to blind luck, right? Now I'll take that because that kind of means there's 99.5% chance that it's down to our model. So checking those two things, right, are correct, then we can be pretty confident that we can go on to use our model, our linear model now for making a prediction. So to make a prediction, who can remember from school the equation of a straight line? Y equals mx plus c. Excellent. Statisticians, because we're all gits, right, don't use that model. What we use is y equals a plus bx. For those of you who are quick-witted, you will realize that that is exactly the same thing. We just move the coefficients around just to piss you off. All right? That's the only reason we did it. All right? Okay, so it's not the only reason we did it. Right? There is a good reason behind it. All right? If I take my pointer here, this is basically the thing we're conditioning on. Okay? And it's nice and clear like this. Let me move my. This would be nice and clear if we're only using one condition, okay? But very rarely instances will you be conditioning on just one variable, all right? So you might have a list of 10 of these, right? So it'll be you know, b1x1 plus b2x2 plus b3x3 yada 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 yada. And once you've done all of that stuff, it's very easy to forget to add that thing on the end. All right. So what we say is, look, do it first, right, before you forget, right, because we know what you like, right? You'll forget. Do it first, then add on all of that stuff afterwards, right? That's why we move the coefficients around. But the point is, that's all we've done. We've just moved the coefficients around. It's exactly the same linear equation. So, having that linear equation, let's go and predict ice cream sales at, oh, I don't know. What have we got? Let's do 18.5 and see what it comes up with. Right, so we want to predict the ice cream sales for temperature of 0.5. So what we need is A, which is the intercept, which is going to be this thing down here, plus the coefficient of that, of the temperature variable, the temperature condition, which is this part here, times the thing we said we wanted, and we did what, 18.5 or something like that, doing 18.5, there we go. And we reckon we will do 118 ice creams at 18.5. So let's go and see if that's about right. So there's 18, it says 110. There's an 18.7 there, look, at 117. So 18.5, 117.5, 118, it's in the ballpark. That's a pretty good prediction, all right? So that's how we can use, linear regression, which is the next spell that we've done, to make a prediction on things which are strongly correlated, in like, you know, ice cream sales and temperature. Okay. Let's close that down. No, don't bother saving that. Let's go on here. All right, so that was cool, right? We can't use that. All right, we can't use that for what we want to do, and now we're going to answer your question, sir. All right, and the reason that we can't use that is because that was a linear regression, right? The trouble with a linear, not the trouble, the thing about linear regression, this screen really needs to be higher, right? As I said, don't be scared to stand up. The thing about a linear regression is there's a line which is the best fit, right? And we do this kind of standard deviation, which we said, you know, what's the difference between where it should be. And actually what we're doing is we're saying, well, you know, given that that line is the best fit, and we know about these points, if I put a point here, or, you know, if I put a point there, what is actually the predicted, where is predicted this line going to go, right? And that's fine for doing things like ice cream sales and temperature, because temperature could theoretically go on and on and on forever going up, and go on and on forever going down. Okay, so it can go on this way forever, and it can go that way forever, all right? We've already said our predictions can't, because probability is constrained between 0 and 1, right? We can't have this going on forever, right? We can't have something that says we've got a 327% chance of winning, yay, right? That's a nonsense, right? Can't be any higher than 100%, can't be any lower than 0%. And linear regression doesn't allow for that, okay? However, what we want to use is the next spell that we want to cast. And we are going to use this thing called logistic regression. It's called logistic regression because everybody recognizes this curve from school. Remember, this is the logistics curve, right? And what happens is now it is constrained between 1 and 0. Okay? So we can use a logistic regression to do exactly the same thing as I've just shown you, but constrain the answer between 0 and 1. Okay? And here is the nice, simple equation for doing that. All right? Now, at first glance, this looks horrible. Okay? But actually, actually it isn't. Because remember, before we were talking about the linear regression, all right? And we said linear regression was just b plus all of the sum of all of the conditions and the coefficients multiplied together. Remember, we said that for linear regression. Well, that's just this bit, right? So we already know that, right? And this bit, this 1 over e raised to the power of that, okay, is just the bit that does the logistic regression, right? Does everybody know what e is? Yes, it's the letter before f. Okay. No, it's 2.7 for the one of better word. It's just one of these constants like pi that you learn. Okay, it's actually the base of the natural logarithm. All right. So we use that 1 plus. So we know that 1 divided by something slightly bigger than 1, right, can never be bigger than 1. All right. So that's how we've constrained it. All right, and we've constrained it there by applying a logarithm. All right. I've got a client I work for, okay, and he says logarithm when he means algorithm in sentences. Do you know it took me ages to work out that that was just a slip of his tongue. It was just a malaprop that he used, right? And for the number of times I walked away from meetings from him going, how the hell does he use logarithms to solve that problem? And then I realized he was just talking bollocks, basically. All right, so that's awesome. That's an awesome. And as I said, dude, you need to show me a concrete example of that. All right, because that's painful. Okay, so Excel won't give us those coefficients, right? You can. That's a lie, right? You can make Excel do everything, right? You can make Excel do that, but there's no add-in for doing it. Okay. So we're going to use another piece of magic that we like in the data science world. We're going to use a lovely piece of magic called R. So if you go in here, we'll use R to do our regression.
There's nothing built into C# for it?
I say again?
Nothing built into C#?
Do you know what there probably is? The question there, just for the benefit of the video, was isn't there anything in C# that does it? Do you know what there probably is? But what I want to do is I want to give you a nice basic introduction. And I don't just want to stand here throwing spells out, so I've hung it all on this horse racing thing. So I want to introduce you to R. There probably is something you can do in C# with, but there seems to be, the data science community seems to favor different tools for doing different things, right? So for computational linguistics and quite a lot of data science, for example, the tool of choice is Python, and the packages in Python for doing data science in general and computational linguistics in specifically is immense. And so they've kind of grown around that, and it's the same for doing statistics. Okay, for statistics, they've kind of flocked around R, and there's loads of packages around R. So even if there was something in C# to do this, it's definitely worth your while if you want to get into statistics and data science and stuff like that to actually learn R, because the next thing and the next thing and the next thing there might not be something in C# for, but there definitely will be in R. Plus, this is dead simple.
Can I have a small comment? It might not be the case with the new C# because it used to be like that because there were no good mathematical libraries for C#.
Mm-hmm.
There were no good libraries for matrix manipulations, for instance.
Mm-hmm.
And I think with the new version that will be out this year, they fixed that.
Yep. So not shipped yet then?
Yeah.
Okay. So to answer your question, no, but coming real soon. And if not, see him, right? Because he promised you really good mathematical and statistical libraries in C#, right? So take his name and his email address, and when C#6 ships, right, if it doesn't have what you need, you get right on him, right? Okay, what we're going to do is we're going to use a bit of R. Those of you who've not seen R before, it looks horrendous. Sometimes it looks a bit like Perl, right? Any language that looks like your cat has jumped on the keyboard, right, is just wrong. So R does take a bit of getting used to. But it isn't that difficult. I'll walk you through it. So what we're going to do here is we're going to create a data frame. We're going to create it by saying, I want to read in a CSV file, and by the way, the CSV file is here. That's just where it lives. Okay. Then I want to head the data, which basically says I want to see what's in that data, right? So we'll just kind of run that just now to let you have a look, right? So that's what that does. So actually what we're doing here is we've got the win-loss, you know, the logistic part of thing, the binomial thing, it's either one thing or another. It's a win-loss. We've got the horse's mile time here, and we've got the horse's weight. Okay, cool. So that's what it looks like. Then we say, dear R, I want to use the GLM function, or the generalized linear model. Okay, and using the generalized linear model, I would like you to calculate the win as a function of the mile time and the weight, using the data that I just gave you, and I want you to use the binomial family of linear models, i.e., I want you to come out with a percentage, you know, win-loss. I want you to predict 0 and 1, right? And then actually what I want, and bearing in mind that what I'm going to get from that is actually, because we've constrained it by the logarithm, remember, we're constrained between 0 and 1, what we're actually going to get is the logarithm of the actual coefficients that we want, okay? What we have to do then is then raise that up to actually get the proper coefficients, all right? So if we run all of that, which is very few lines of R, then what we'll get here is down here, and we'll see we'll get our intercept, and we'll get our coefficient for mile time, and we'll get our coefficient for weight. And then all we have to do is to put it back. Actually, we can make R do this, but if you wanted to do that, I want to tie this up to the actual formula. So if you remember the formula that we had before, that's your intercept, and those are your coefficients that you put into that same linear model that we had, that same linear equation, except then constrained by the logarithm by that 1/1 plus part added to it, okay? And that answers your question. Because we've got ones and zeros, how come you can do that regression, that same thing that we did with ones and zeros and natural numbers, which are really categorical? The reason we do that is you're right, we can't, so it showed we couldn't use the linear model. What we have to use then is a log linear model, or a logistical model, or actually sometimes there's a probit model. It's all basically the same thing, okay? And that's how you do that. And that's also introduced you to R for very good statistics language. Okay, 10 minutes to go. See, we've got kind of sidetracked now, and now we're running out of time. So let's do this last bit really quick. Dun, 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 dun. All right, so what happens if the relationship isn't linear, or you're using lots of different functions, some are linear and some are not? Okay, what are we going to do when we don't know the actual, whether it's linear? It just could be, you know, quadratic or whatever, right? And here we're going to use Bayes' theorem, right? I don't like Bayes, right? The reason I don't like Bayes is because he came up with a mathematical formula which basically drives statistics to this day. It's at the heart of machine learning, it's at the heart of data science to this day, and he died in 1761, and he didn't even have the goddamn good grace to be a mathematician, right? He was a man of the cloth, right? There's just no need for that, right? There's no need for smarty pants people like that. However, he did leave us with an awesome formula. And this is it here. It looks horrendous when you see it written down, right? But it's just because you need to know what the syntax says. And basically, in abstract, what that syntax says is, what is the probability of event A happening, given that, that's what the bar means, given that event B has happened, right? And that equals, well, what is the probability of seeing event B when event A happens, times the probability of event A happening on its own, all normalized for event B happening regardless, right? Now, I just explained that to you, right? It all is totally meaningless because it's meaningless and abstract. But for our particular concrete example, what we said here is, what's the probability of horse A winning given that jockey B is riding it? So, well, in that case then, how many times when horse A won was jockey B riding it? All right? Times what is the probability of horse A winning regardless of who's riding, divided by what is the likelihood of jockey B winning on any horse? Right? So that's basically what that means. All right? Everybody understand? Awesome. And that's such a simple theory, right? Such a simple theory, but it's so mega powerful. Right, what we're going to do here is we're going to very quickly just have a look at this because we're running out of time. So if we grab this and we use Bayes, right? Here I want to know what is the probability of our horse winning given that he's coming out of stall 6, all right? What we do here is, we need the probabilities of, what's the probability of him getting stall 6? Well, there's 8 horses, so it's a 1 in 8 chance. Probability of him not being in stall 6. What was the probability of him winning from stall 6 and not winning, and not in stall 6 and winning, and not in stall 6 and not winning, right? Now basically they all have to balance, right? So there are couples of mutually exclusive things, right? So in stall 6 and not in stall 6, right? Winning from stall 6 and not winning from stall 6. They're mutually exclusive, you can't do both. And the probabilities must add up to 1, right? This second bit is only for me because I'm really good at missing the pairs, right? I'm very bad when I'm doing Bayes at leaving off one of the pairs, so I just do in a set here to make sure I've got them all and they all add to 1, right? And then I just do that piece of formula there, okay? And then I push out the probability into our chart again, all right? I'm not going to bother running that because we're running out of time, okay? And basically it's just going to show another probability on the chart, right? But this is the important part for Bayes, right? You need to know all of these probabilities, right, for working out Bayes. But it's easy because they're mutually exclusive, right? So it's just stall 6 and not in stall 6, and winning from stall 6 and not winning from stall 6, all right? Okay. I will run it because it's cool. All right. So actually, we've got a 6.1% chance of winning just because he's running from stall 6, right? Okay, so he obviously doesn't like that stall. Okay, so you'd probably not bet on him. If you saw that horse was starting from stall 6, you'd probably not bet on him. All right, so that's that. All right, let's go back to the slides. Okay, thank you, I've just done that. Right, massive day of learning, massive day of learning, right? This is probably like a whole semester in Statistics University, and we've done it in 90 minutes, so if you've stayed awake and you've followed it all, right, congratulations, right? This is everything we've learned. The difference between prediction and a guess, naive and conditional probability, why it's important to build a model, average is the simplest model, standard deviation tells you how well fit is. The average without standard deviation is a meaningless number, right? People tell you what the average so-and-so is, ask them what the standard deviation is, and if they can't tell you, then tell them they are wasting your time, okay? Then we went on to the difference between qualitative and quantitative data. Then we talked about how to bin qualitative data so we can still be useful. Then we talked about weightings in Unity, how to add weightings to our actual models, and then what we have to do to get back to Unity after we did that. We talked about linear regression, how straightforward that was. We talked about logistic regression because what we actually had was a binary prediction, so we can't use linear regression, we're to use logistic regression. And then we talked about Bayesian statistics for things where we don't know that there's a linear relationship between the two things, right? Massives we've learned today, so thanks very much for staying with it. We do have 3 minutes, right, remaining for questions. If you do have a question, then please, stay behind to ask it. That's absolutely great. If you don't, I'll let you out 3 minutes early so you can get onto the beer. All right. But thanks very much. And if that's whetted your appetite, I hope to see you on Thursday for troll hunting, which will basically go into this, but in a lot more depth. Bayesian statistics, right? We're going to really go into Bayesian statistics, and we're going to write our own Bayesian classifier, but we're going to hook that up to the story of troll hunting, which will be really interesting. And so hope to see you on Thursday at 4 o'clock. If not, thanks very much for coming. There's my blog down there as well. And lastly, is my Twitter handle there at the bottom. I guess everybody's on Twitter now these days. Please feel free to follow me and ask your questions there if you want. I much prefer to answer questions and deal with people initially on Twitter. Not because I'm always on Twitter, it's just that your question can only be 140 characters long if you're using Twitter, and that suits me just fine. Instead of screeds and screeds of emails that basically say, please will you write my code for me? The answer to that question is yes, it will just cost you a lot of money, that's all. But I absolutely will write your code for you. Okay, so what are we going to do here today? Today we're going to do a gentle-ish introduction to data science and all that nice stuff. So we're going to cover a whole bunch of statistics. We're going to cover a little bit on machine learning around Bayesian inferencing. Those things are what a friend of mine calls spell casting. He says you recognize a problem and you go, aha, this is the linear regression spell I have to use here. I shall cast that spell. Okay. The trouble with that is, if I just stood here and went, here's another spell, learn that. Here's another spell, learn that. It's going to be pretty dull, okay? So we are going to do that. We are going to do that. Hopefully it's not going to be dull, all right? But we're going to hang all that stuff on this idea of predicting who's going to win horse race, right? So we're looking at prediction, we're looking at predictive analytics, we're looking at predicting the result of a horse race, but we're going to cover a bunch of statistics and start to get into the machine learning with Bayesian statistics towards the end. We're going to look at that as well. If you've got any questions, please ask them at the time. Don't feel you have to run over 2, therefore it's 50%. Okay? You can only use the naive probability formula if all outcomes are equally likely. Okay? That last bit at the end, which says we can only do it if all outcomes are equally likely, means that naive probability falls down fairly quickly. Okay? A great example of where it falls down is if you say to me, well, I'd like you to calculate for me the probability of there being intelligent life on the moon. Okay, I'll say, well, that's not the problem. It's simply the number of winning outcomes, which is 1, because there either is or there isn't, or over the total number of outcomes, which is 2. So there either is or there isn't. Therefore, the probability of intelligent life on the moon is 50%. Right? It isn't, okay? Because there's such a thing as conditional probability. Not all outcomes are equally likely, okay? And that's where we get into conditional probability. And conditional probability is usually expressed in language as using the word given. So, what is the probability of there being intelligent life on the moon given that there's no atmosphere? Okay? So now that we know that, now we can answer the question, what is the difference between a prediction and a guess? So a guess is picking what side of chance an event will fall. Okay? With a fair coin toss, the tosses that came before have no bearing on the tosses that come afterwards. Each outcome, heads or tails, is equally likely, so it really is chance. And if I were to say to you, pick heads or tails, it's really a guess. There's no way for you to predict the outcome of that. Okay? You keep them to the end or anything like that. It's sometimes kind of better if we can get a bit of a conversation going with the audience than just listening to me talk. But if you do want to keep your questions to the end and come up and ask me them afterwards, please do. I'll be here while I'm packing up. I'll also be downstairs afterwards, having a beer or two, courtesy of Amazon afterwards. The sense of the answer that you get varies inversely with the amount of beer I consume. So if you want an in-depth conversation, don't leave it too late in the evening, would be my advice. Okay. So the first thing we want to do is we want to answer this question. What's the difference between a prediction and a guess, right? Because my kids, they make predictions all the time. Oh, okay, they're just guesses, right? The short answer to that from a data scientist, the short answer to that question is about 750 quid a day. Okay, it's the difference between a prediction and a guess. But really, to answer that question, we have to look a bit at probability. The first thing we're going to look at is naive probability, and everybody knows what naive probability is. The formula for naive probability is really simple. It is the number of winning events divided by the total number of events. All right? So the canonical example of that is the fair coin toss. Okay? So if I toss a coin, the number of winning events is 1. You can only event. If I call heads or tails, you can't say heads and tails. Haha, I win. Right? You've got to pick one. All right. So the number of winning events is 1. The total number of events is 2. It can either be heads or tails, and therefore it's 1. So I'm just going to be stood here presenting instead of wandering about like I normally do for 2 reasons. 1, I have to stand close to the mic apparently because they don't have any radio mics. So if I move over here, people can't actually hear what I was saying on the video. And secondly, annoyingly, I've forgotten my slide advancer. So I've got to stand here and actually press the buttons. How 1980s is that? Pressing buttons and stuff like that. It's the first time I've ever given a talk where the room I am actually houses the toilets. And so anybody who wants to go to the toilet has to come into your room to use the toilet. I mean, that's not going to be very embarrassing for everybody, is it? Oh, and we can check if he's washed his hands. He didn't wash his hands. Get a picture of that guy. That's just awesome. All right, so we'll make a start. So these are 90-minute sessions, okay? Maybe a bit longer than you're normally used to at other conferences. Maybe you're not. I definitely won't go late, definitely won't run late, because I understand that I am the only person standing between you guys and beer, all right? And that's never a great place to be, okay? So we'll get through it. We'll finish on time. We may finish a little bit early. Depends how much questions there are, stuff like that. But anyway, just in case you're in the wrong room, all right, this is Data Science for Fun and Profit. My name is Gary Short. Anybody who isn't expecting that talk by me can leave now. All right, failing that, you're trapped and you have to be here for the next 90 minutes. All right, so this is me. As I said, my name is Gary Short. I'm a contract data scientist and data engineer. I'm also an MVP in C# because I was a developer before I became a data scientist, as if those two things are separate. You have to do some development to be a data scientist, so that's cool. Data science covers a broad church, all right? To say you were a data scientist is a bit like saying, you're a farmer. That doesn't really tell people what it is that you do. So I mainly specialize in 3 areas. I specialize in predictive analytics, which is what we're going to be doing today. I specialize in computational linguistics. We'll touch on that a little bit on Thursday's talk when I talk about troll hunting on the internet. So on Thursday's talk, we are going to talk about how we can identify, how we can basically remove all the nasty trollish posts that appear on Twitter and Facebook, how we can make it so that those never appear. Okay, we'll do a little bit of computational linguistics then. I also specialize in machine vision. We're not going to do any of that this week at any point. The most important part of these slides, the bit at the bottom, really, this is how to get a hold of me afterwards when you realize that you had a burning question but you didn't realize it at the time. You can get me on email at Gary@DurnCodingIt. See what I did there? That's a joke.